Welcome to Astronomy 103. In this segment, we will talk about dark matter. I'll check one thing. The makeup of the universe. Up until now, we've talked about stars, planets, galaxies, black holes. This makes up only about 1 to 2% of the universe. The stuff that shines doesn't only contain most of the atoms in the universe. Most of the atoms is still gas. Here's the makeup of the universe. There's atoms, less than 5%, dark matter around 23%, dark energy around 72%. So about 95% of the universe is what's called either dark matter or dark energy. All right, 23% of that is dark matter. We don't know what dark matter is, right? It's unlike anything else we experience. Ordinary interacts with ordinary matter and with light. Dark matter doesn't. Its only interaction is through gravity. Right now, dark matter can only be observed via its gravity. So we have to look at its effect on the biggest objects in the universe, galaxies and galaxy clusters. We can measure the mass of a galaxy by looking at how fast stuff rotates around it. So we talked about this already, in the rotation curves of galaxies. By looking at Doppler shift of gas, stars and gas, we can tell how fast they are moving toward us at different points in the galaxy. Here's Newton's law of gravitation. Any two objects will attract each other with a force given by F is equal to G times m, little m, divided by r squared. Right? And so basically, by looking at how things are pulling toward each other via orbits, you can tell how much mass there is, how much m's there are. Right? So rotation curves of galaxies. So what we find is that we move away from the center of a galaxy, the rotation speed tends to flatten to a constant speed. Right? So what that means is the mass of the galaxy continues to increase even in areas where there are very few stars. So here's an example. There's apparently more mass beyond the outer regions of this galaxy than there are in the inner parts, even though only inner parts shine. So there's some hidden matter or dark matter that's adding to the gravity of this galaxy. We can use individual galaxies and their orbital speeds to infer the masses of galaxy clusters, which are the biggest structures in the universe. Typically, galaxy clusters contain thousands of galaxies, many of them as big or bigger than the Milky Way. So here's an example of a cluster, lots and lots of galaxies there. All right. So by looking at the redshift and blue shift of lots of galaxies, we can figure out how fast they are moving on average. Right? And one of the first people to do this was a guy named Fritz Zwicky, whom we already know from neutron stars. He was a great astronomer, but he was also known for his caustic personality and wit, which made him not too popular with his Caltech colleagues. In particular, he used to call them spherical bastards, right? Because they were bastards no matter what angle you looked at them. Right? So the cluster that Fritz looked at was the Coma cluster, and he noted the speeds of the galaxies suggested that the mass of the cluster was 100 times bigger than the mass of all the galaxies he could see. Now, most of the matter in galaxy clusters is actually not in galaxies. It's actually in gas or intracluster gas, which is very, very hot, up to basically 4 times 10 to 8 or 4 times 10 to 7 degrees Kelvin. Actually, sometimes 10 to 8 degrees Kelvin. But even this gas itself is not enough. So here's an example of intracluster gas. This is ABO 2199. There is basically gas around it, seen in this X-ray image from Chandra. And basically there's the optical image of it. And see there's lots of gas where there's not a lot of galaxies. So there's still more matter or more dark matter that is contained in this intracluster gas. Right? So the combination of all these measurements means that there's a lot more gravitating mass than there is visible mass in the universe. So we look at the flat rotation curve of galaxies, the orbital speeds of galaxies and clusters, gravitational lensing. So collectively, this matter is known as dark matter. It's generally thought to be a particle that doesn't interact much with an ordinary matter, but it might be more than one particle. It might be many particles. We don't really know. Right. So in fact, galaxies and galaxy clusters sit in the middle of a collection of dark matter, which is known as dark matter halo. This dark matter halo is actually much bigger than the galaxy, at least stretching for a distance at least 10 times larger than the galaxy itself, and usually 10 times bigger than the size of the galaxy cluster itself. All right. So let's talk a little about galaxy formation and evolution. So the first thing we talk about, stars don't really collide. Space between stars is much, much larger than their sizes. But the space between galaxies is not so much larger than their sizes. So galaxies in fact do collide. In fact, on average, they collide once during their lifetime. All right. So basically, every galaxy will collide with one other galaxy during its lifetime. Here's a picture of so The galaxy collision can produce many interesting galactic morphologies. Here's a picture of the Cartwheel galaxy, so you might wonder how it got its shape with the outer rim and the spokes. Well, it's thought to be a result of a collision by the center of a much smaller galaxy. I had a computer simulation for this, but unfortunately skip it. Here's another one. This is called the Antenna Galaxy, all right? And here, basically, computer simulates how you produce such a galaxy. Two spiral galaxies basically collide with each other, producing a beautiful long antennae, right? And the collision galaxies not only changes their shape, which we see in the Cartwheel and Antenna Galaxy, but also induce very rapid star formation. We see this in Antenna Galaxy, which we just discussed. In the Antenna Galaxy, there's massive star cluster, what we call a superstar cluster, with mass about 10 million times the mass of the Sun. Huge amount of star formation within these superstar clusters here. All right. The most rapidly forming galaxies in the universe, the ultraluminous infrared galaxies, all look like collisions. Right. So collisions generate star formation. Here's basically an example of one. This is a nearby one called ARP 220. Right, and you see there basically it looks like two nuclei of two galaxies. If you look at a collage of these things, of ultraluminous infrared galaxies, all of them basically are either in the process of colliding or basically have lots of nearby galaxies close by to them. So they all look like collisions essentially. So galaxy collision causes galaxies to evolve. It's generally thought that galaxies form by the merger of many smaller galaxies. So small galaxies make bigger galaxies, and bigger galaxies collide to make the biggest galaxies yet. So this process is known as hierarchical merging. Right. There are two lines of evidence for hierarchical merging. First of all, in order for elliptical galaxies, which tend to be the biggest galaxy in the universe, it seems to suggest that you need to merge spiral galaxies to make them. Here's a picture of early universe, shows large number of lower, and also the second thing is that if you look at early pictures of the universe, basically show a large number of lower mass irregular galaxies, which are no longer present. All right. So one particular collision is a collision between Milky Way and Andromeda Galaxy. Here's a computer simulation of that. So there's the Milky Way, basically the bar spiral, and it's flowing happily through space within the local group. There's Andromeda lurking, right? At some point, these two things are going to start to collide with each other, and they're getting closer, 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 and there's a path right there, and there's the collision. Lots of stars get spewed away. What's M32 going to do? Another collision here. And now rapidly the two nuclei will merge and you form a lot of stars that are thrown out, and basically an elliptical galaxy is formed. Okay, the collision between the Milky Way and Andromeda, which are two both spiral galaxies, will produce an elliptical galaxy. This collision will destroy this and mix with the orbit of stars, producing ball of stars called elliptical. It's generally thought that you have to collide two large galaxies to produce elliptical galaxies. Collisions between two galaxy compartments are called major mergers. Collisions between big galaxies and small galaxies are usually called minor mergers. The galaxy collision not only fuels star formation, but can send a huge amount of gas to the center to fuel the central supermassive black hole. And the energy emitted by these accreting supermassive black hole can blow out all the gas in galaxies. This process is known as feedback. Right? There's some evidence for feedback. One line of evidence for this feedback comes from a close relationship between the mass of the black hole and the mass of the galactic bulge. So if you basically plot the mass of the black hole, mass of the galactic bulge as opposed to mass of the black hole, what you find is that it follows some kind of straight line here. So how does the black hole know about the mass of the bulge, which is typically about 1,000 times more massive? Right? Well, it has to basically influence somehow. Right? So what's thought to happen is that like when you form the bulge, they're forming in the same way. When you form the bulge by colliding two galaxies together. Here's a collision of two galaxies, right? And it's gonna basically have a first pass, draw away, lots of gas getting funneled to the center now, fueling up black hole, fueling the growth of the black hole. Now this thing will basically come back again and basically generate another collision. See that happens. So these black holes are growing, growing, growing. And basically what's happening is it's starting to blow away the gas. Right? The black hole is generating so much energy, it's blowing away the gas. Now this thing, if you see in stars, you see a second collision here. This will generate more gas, fire more gas in the center, and generate one final titanic explosion that will blow away the rest of the gas, and all the gas is gone. Now, there are lots of stars, so here you can't see them. The only reason why is that this thing is only applying the gas and not the stars. And so all the gas will get blown out at some point, leaving nothing behind but just a bunch of stars and the empty black and the black hole in the center. Okay, so as a black hole accretes gas, it shines as brightly as a quasar, which we encountered in the llast chapter. So recall the friction of the gas forming a black hole causes the gas to shine brightly, right? And because every galaxy seems to have a close relation with its black hole, right? That means every galaxy must have been a quasar at some point. It has to be a quasar and it'll blow all the gas so you stop forming stars in the bulge. So every galaxy has its own quasar epoch, right? The quasar epoch happens soon after galaxy collide. So quasar hosts should all look like collision. And indeed, this seems to be the case, right? If you look at basically a Hubble collage of these things, a lot of these objects, these quasars, appear to be disturbed galaxies like that one, this one, this one, this one, this one, or collisions, right? So here's basically a picture of galaxy formation evolution. You have mergers. These are mergers of small galaxies produce basically larger galaxies. You have central black hole. Sometimes basically you have a minor merger. You have produced basically normal spirals. If you have a major merger between equally massed galaxies, then basically you have a really, really powerful galaxy which basically blows out all the material and you generate a normal elliptical in that case. All right. So basically galaxies from the emerge from the merging of many small galaxies, the Hiroko merger picture, and the major merger produce starburst galaxies, quasars, and typically elliptical galaxies. Minor mergers can fuel a Seyfert galaxy, which is a much smaller version of a quasar, and leaves disk intact, so we have spiral galaxies there. Okay, let's talk a little about large-scale structure. The universe turns out to be organized on larger scales. So stars are organized in galaxies into clusters, clusters into larger structures called superclusters. Okay. The Milky Way, Andromeda, and several other clusters form the local group, which is small galaxy clusters, right? The nearest large galaxy to ourselves is called the Virgo clusters, and the galaxy clusters themselves tend to clump together into superclusters. The Virgo cluster, local group, and several other nearby clusters are formed the local supercluster, right? So here's the local supercluster, right? There's Virgo, so we're part of this thing. There's Ursa Major, there's Ursa Centaurus right there. It's a big collection of this stuff. There's nothing there, right? So everything gets concentrated in certain regions, right? For the map of the local supercluster, you can see that galaxies are lined up into lines of filaments. So this happens to be true in larger scales. And you basically see this in large-scale surveys of galaxies called redshift surveys, right? So by basically pointing the telescope at a certain direction in the sky, we can figure out where the galaxy is in the sky. And by looking at spectral lines, you can tell how far fast the galaxy is receding us. And using Hubble's law, you can figure out how distance to these galaxies. And so basically one example of redshift survey is a very famous one known as the Sloan Digital Sky Survey, or SDSS. It's measured the spectrum of about, well, now this number is dated, 1 million galaxies. Now it's close to about, I think, 4. And about 120,000 quasars. I think this is close to maybe 1 million now, actually. It's the biggest data set in astronomy. That's still true for now, right? Okay, so there's large-scale structure. You see all these large-scale structures. You see the Great Wall right here. These are voids, regions which are completely empty. All right, there's a Coma cluster right there. All right, and the universe organizes these great filaments on a large scale review by the redshift surveys. They're also basically these big empty regions known as the voids. The size of these structures can be very large. The filaments of voids can top out around 200 megaparsecs or so. All right, the company of this universe is explained by dark matter. So dark matter interacts only through gravity and naturally gravity causes things to clump up. And computer simulations of dark matter naturally produces this cosmic rays. So strong evidence that the universe is filled with dark matter. So here's an example of such a thing.
Big Bang theorists believe that the universe has been expanding for 15 billion years. In this historic scientific simulation, generating over half a terabyte of data, the computational grid refines in space and time to yield small-scale features. We see gravitation forming nested hierarchies. Tiny fluctuations in the density of the early universe are amplified into a network of interconnected filaments. Along these filaments, condensing gas clouds give birth to new stars and merge into whirling galaxies. Galaxies congregate into clusters, colliding, merging, and forming new galaxies in a fiery cosmic dance.
So notice how the dark matter halos tend to combine with each other in simulations. So galaxies follow dark matter halos will also combine with each other as a result. So galactic collision is a natural result of dark matter universe. So by clumping together via gravity, dark matter carries galaxies so that they collide with each other. Because we see the effect of dark matter via the gravity, we can also see their gravity distort light. So we call Einstein's theory of general relativity. So gravitating mass can distort the path the light takes. And so by constantly distant light to us, this gravitational mass can act as a lens or a gravitational lens. Right. So here's an example illustrated. Light path, which is diverging, basically gets converged to us because of a central mass in the center, like a galaxy, for instance. Right. And gravitational lensing, as we mentioned before, is seen in many clusters of galaxies. So for instance, here's the background guys stretched out as objects because of the mass of this galaxy, mass of the galactic cluster. Right. Here's another famous lens, is known as Einstein cross. Right. So basically, this is a background quasar being lensed by a galaxy here. So you have 4 different images of the same quasar. Right. Here's a few other examples of galactic gravitational lenses. A few of them are actually really nearly perfect. Right. So these are the Einstein rings. These lens galaxies are almost directly behind the lens galaxies are almost directly behind these galaxies, and so they appear as almost a perfect ring in the sky. Right. So these previous slides were examples of strong galaxies. It's strong because it's quite obvious, but you can also measure distortion of galaxies. You can also map the dark matter between galaxies, right? So here's an example of this. One such map is a cluster known as a bullet cluster. It's merging as 2 clusters. The red contours basically show where the dark matter is, and I think the yellow contour essentially shows basically where the gas is. Right, so the gas is displaced basically from the 2 galaxies. Right. The bullet cluster is really interesting because you use the X-ray to tell where most intercluster gas is. Where intercluster gas is what makes most ordinary matter. So we plot this out. The ordinary matter is in red, dark matter in blue. Look at that. So there's the dark matter. There's the ordinary matter, and look, it's like this gas here is being left behind, right? So the ordinary trails the dark matter, almost gets left behind. This shows that most of the matter in the cluster is not ordinary, but rather matter doesn't interact with ordinary matter. So almost proof positive of the existence of dark matter. Okay, so let's talk about weak gravitational lensing, right? So most galaxies are not lensed very strongly. Instead, they're only slightly distorted by matter, particularly dark matter in the foreground. So you measure this very slight distortion, you can map the dark matter. So here's an example of that. So what you want to look at is distortion in shape, right? So basically, this is a bunch of galaxies here unlensed, right? And you put some lenses in front of it, and you see there's some distortion in the shape of the galaxy. So you can measure the distortion then, right? Then you can measure a little bit about, infer the existence of basically dark matter in front of these material, right? So for instance, you're looking at very, very slight distortions of these lenses on the sky. Now the only problem is that galaxies are already really weirdly shaped. So what do you mean by distortion? So you need a lot of galaxies, and you assume they're randomly oriented. So this turns out to be extremely hard to measure, but there's still some progress. The measure is still highly uncertain. But if you do so, you can create small maps of basically what the dark matter is in the universe. So here's an example from the Cosmos survey. All right, so you get 3D maps basically of the dark matter from this way. And